Hello everyone. Welcome back to Dr. Liu's VCE Physics channel. Today, let's learn together about the 2025 physics examination. We will focus on questions related to the photoelectric effect. My explanations may not be perfect. If any teachers, parents, or classmates find errors, please feel free to provide your guidance. Jessica and Matthew investigate the photoelectric effect. They expose a metal sample to light of constant intensity, but varying frequency, and measure the voltage required to stop the most energetic electrons. This allows them to calculate the maximum kinetic energy, max, of the electrons. The data collected is plotted and a trend line is drawn, as shown in Figure 20. This question is a classic VCE physics task focusing on the photoelectric effect and the interpretation of experimental data. We use the syllogism approach to meet the specific marking criteria. 1. Physics context, the premises. The equation. The photoelectric effect is governed by Einstein's equation. The mapping. On an max versus frequency, f, graph, this takes the linear form. Y equals mx plus c. The identification. Therefore, Planck's constant, h, is equal to the gradient of the trend line. The hook. Don't just crunch numbers, interrogate the graph. The line is the truth, the dots are just noise. The gradient is Planck's constant. The action. Ignore the data points. Pick 2 clean spots on the trend line itself. Let's use 15, 4.4, and 25, 8.8. Our rise is 4.4 electron volts. Our run is 10 units, but check the x-axis. The frequency is measured in units of 10 to the 14 Hz. The result. Divide them. 4.4 divided by 10 to the 15 gives us 4.4 times 10 to the 15 electron volts s. That's your 2 marks, one for showing the gradient method, and one for the accurate constant. Fast, clean, and examiner proof. The concept. In the photoelectric effect equation, the work function is the y-intercept. It's the energy debt the electron must pay before it can even leave the metal surface. On our graph, this is simply where the trend line hits the vertical axis when the frequency is 0. The action. Look at Figure 20. If we take our ruler and extend that solid trend line backward, extrapolate, until it crosses the vertical axis, where does it land? It hits exactly at 2.2 on the energy scale. Since the work function is defined as the magnitude of this intercept, the energy required, which is a positive value, our answer is simply 2.2 electron volts. Pitfalls, Planck's constant. The line versus dot trap. Using raw data points, the black dots, instead of coordinates exactly on the trend line. The origin error. Calculating h for 1 point. You must use the gradient formula with 2 points, because the line doesn't start at 0, 0. The power of 10 miss. Forgetting the 10 to the power of 14 multiplier on the x-axis label. This leads to an answer that is 14 orders of magnitude off. The unit slip. Failing to state units as EVs, as indicated by the y-axis in EV. Pitfalls, work function. The textbook reflex. Using 4.14 times 10 to the power 15 from your data sheet instead of the specific evidence shown on the experimental graph. Formula over complication. Get the work function when you can simply extrapolate the line to read the y-intercept directly. The sign mistake. Giving a negative value. The work function is an energy requirement and must be positive, 2.2 electron volts, not 2.2 electron volts. Scale misread. Miscounting the minor grid lines on the y-axis. The minor grid on the y-axis is 0.4, and we estimate the half of 0.4, which is 0.2. In physics exams, the graph is king. If the graph's line says the constant is 4.4, don't argue with it by using your calculator. Trust the line, read the axis carefully, and always check your powers of 10. If you need my help, you can add me on WeChat or WhatsApp, or send me an email. Thanks for your attention. Please note Dr. Liu's VCE Physics channel, Dr. Liu's VCE Chemistry channel, and Dr. Liu's VCE Biology channel.